Hi everyone, and thanks for tuning in to our lesson on volume of solids of revolution with disks. If you haven't already done so, be sure to jump onto Schoology under Unit 5 videos and watch the 2 videos that come before this one that you're currently watching for some good visuals and graphics that I copied from YouTube. But for this lesson, after you've watched those other videos, we're going to start with some vocab. So we need to know, in order to get through this lesson, what a cross-section is. So I've already written the definition out, and you can pause the video to write it yourself, but here's what it says. A surface or shape that is or would be exposed by making a straight cut through something. Okay, so you have to envision a 3-dimensional object, and then you basically take a knife, cut through it, look down into the object, and what do you see? That is what a cross-section is. So the video that you watched already, let me grab a separate sheet of paper here, showed some different objects and their cross-sections. So like, for example, say you had a cylinder. If you had a cylinder that was solid, and you cut right through it, and you were up here looking down in, what would you see? Well, hopefully you can envision that you would see a circle. Cross-sections will mimic their bases. So kind of like if you pick the object up and look at the bottom or the top, the cross-section often is going to mimic whatever shape that is. What if you had a cone? So say you had a cone that was solid. You know, think of like if you made it out of clay or even almost like a Hershey Kiss or something, even though they're not perfect cones. But if you cut into it, and then you say you were standing here and looking in, or you were standing here and looking in, what would you see? Well, hopefully you can envision that you would see a circle. So oftentimes, cross-sections of 3-dimensional objects are circular, and in this lesson, we call that a disk. So I'm going to highlight that word disk because this lesson will only deal with cross-sections that are disks. Okay, so let's take a look at example 1. Example 1 says, find the volume of a cone with a radius of 4 and a height of 4 using geometry. So we're going back a couple years here in your math studies, but here's the formula I reminded you. Volume of a cone is 1/3 pi times radius squared times height. So I've got that set up here, and I'm just going to plug in the radius here, which is 4. So 1/3 pi times 4 squared, and then times the height, and the height is also 4. So I'm going to fill a 4 over top of that H. And I'm just going to go to my calculator at this point, and you can too. And let's type that in. So 1/3 pi, times 4 squared times 4. And I'm getting 67.021. So I'm going to write that down. 67.021. Okay. Let's go to the next example. Example 2, find the volume of the solid generated. That's interesting. When the region bounded by y equals x and the x-axis from x equals 0 to x equals 4 is revolved about the x-axis. So what I've done here, and again, you can always pause the video if need be. I've already drawn this for us. This right here is the region bounded by y equals x, which is right here, the x-axis moving from x equals 0 to x equals 4. So it kind of forms this triangle shape here. Now, what we're going to do is we're going to spin or revolve this region around the x-axis. So what I like to do is, here's the x-axis. I'll often draw myself this little shape. It's like a little loop-de-loop with an arrow just to show that I'm spinning around the x-axis. And when I do that, I like to actually reflect my region across the x-axis. So I'll kind of make a mirror image here coming across. Now, of course, this is still drawn in 2 dimensions, but it helps me to envision that if I was spinning this around the x-axis and I wanted it to be a 3-dimensional figure, it helps my brain process what that would look like. So let's think about that. You watched that video on volume and cross sections. Can you envision what this shape would be in 3D if you picked this region up and started spinning it around the x-axis, kind of pausing it and moving it around? Hopefully, your brain is telling you that it would look like a cone. So we've got ourselves, if I just pull this out to the side, you know, we've got ourselves something looking like this in 3D. Okay, so we've got a cone. Now we've talked about the cone and what its cross section would look like. If you sliced the cone perpendicular to the x-axis, so slice it or bring your knife in perpendicular to the axis you're revolving around. So if you make your cut and you were over here looking inward to your shape, you would see a circle. We're going to call that a disc. All right, so each disc, what we're going to do here, each disc that represents a cross section is going to have this circular shape here, and it's also going to have some thickness. The thickness I'm going to draw like this. This is what truly makes a circle turn into a disc, okay? Now the disc, this disc right here, has a volume. The volume of this disc would be nothing more than the volume of a cylinder, because really this is just a cylinder with a really small height. So the volume of a cylinder is pi r squared h. So in our case, pi r squared, now the h, do you see how this is running horizontal? Well, that height, if I move this over here onto my drawing here, if I draw a cross section, that's a disc, then what turns out happening is my height of that disc running right here is just a little change in x because it's parallel to the x-axis. So my height becomes dx. So the volume of just one cross section of this 3-dimensional shape we've created with rotation is equal to pi r squared dx. So the idea to find the volume of this cone sort of laying here on the x-axis, the idea, going back a unit, is to add up all of the discs from 0 to 4, add up all those volumes. If you add volume plus volume plus volume plus volume plus volume plus volume, you get volume, and add up all of them to create the whole. Think about Riemann and his rectangles. When we were doing Riemann sums, didn't we add a bunch of rectangles, an infinite amount of rectangles, to fill the space and create the total area? We're doing the same thing, but instead of using rectangles to create area, we're using discs to create volume. And the shortcut to adding up an infinite number of rectangles was to use the definite integral. So the shortcut to add up a bunch of discs is going to be the definite integral. So watch how easy this is. We're going to integrate from 0 to 4. Each disc has volume right here. So I'm going to bring this up, pi r squared dx. There's separation there. That's pi r squared dx. And this is going to give us our total volume because we're summing up a bunch of little volumes. Now the last piece of this, if you want to go to your calculator to figure out the actual number, we actually need to find r, the radius of our discs, in terms of x. we have too many variables right now. We can't, if I would try to do this, if I try to take Math 9 from 0 to 4 of pi, and then type alpha r. Where's my r? Where's my r? Jeez Louise, where is my r? There it is. Alpha r squared, and then dx. It's going to give me 0. It doesn't even make sense. I probably have something stored in the variable r somewhere. This isn't going to work. You need to have your definite integral all in terms of x's. So now what we have to do is get the radius of a cross section in terms of x. So to do that, check this out. So the radius of a cross section is going to run from the center of the circle out to the circle's edge. In this one, it would run from here to here. Now, coming over to the graph, we're talking about the x-axis being the center of the cross section out to the edge of the circle. But where's the edge of the circle? Well, the edge of the circle runs along the line y equals x. So the radius of any cross section, the little ones, the big ones, and everything in between, is just going to be y equals x. So even if you draw like a little cross section right here, the radius is still going to just be from the x-axis up. And if you draw a bigger one out here, it's just going to be defined by this top function. Okay, so to finish this off, this is what we're going to have. We're going to have v equals the definite integral from 0 to 4 of pi, here we go, the radius in terms of x is just x. Now, I want you to think of this, though, as really being, the radius is really the x minus 0 squared dx. So where's this minus 0 coming from? Well, since the distance between this line and the x-axis would really be the top function minus the bottom function, we want to think of it as such. Like, we definitely want to do top minus bottom to get that distance. So I'm going to put the top function minus the x-axis, which is just the line y equals 0. That's where I'm getting the 0. And even though it doesn't seem necessary now, if our three-dimensional object is displaced off of the x-axis, it will come into play. Like, and I'll show you how. So say you have your cone, but now it's like up here. Okay? Now, when you're trying to find the radius of a cross section, what ends up happening is, here's your cross section. Here's the radius. And to get that radius, you'll actually, and I'll teach you this later, you're going to have to take the top and subtract the bottom, because that's going to give you, actually that's going to give you your diameter, and we just want the radius, so then we'll maybe have to divide that by 2. So just keep that in mind. We're going to do top minus bottom. Okay. Oh no, I did that wrong. Oh my gosh, Callahan, what are you doing? No. What I want to do here, forget that bottom thing. What I really want to do here is bring, hold up, let me get another color. I forgot to move the x-axis up. So like, it's almost like you're here now. So this was the x-axis. This will be like the new x-axis, okay? So now when you want to find the radius right here, you would take the top function, which is this guy. That'll give you this whole distance, minus the bottom function, which is this, and that will give you what's left over, which is the r. So maybe this is like, I don't know, maybe we're up here at 3. So it'll be top minus 3. So not that you need to know this for today, and I'm sorry for that hiccup. I didn't mean that earlier part, but we're going to need top minus bottom because we don't always spin around the x-axis. Okay, cool. So here we are. And now I'm going to plug this into my calculator for total volume. Check it out. We've got, pull this over actually here. I'm going to put this in right here. So I'm going to do math 9, definite integral from 0 to 4 of pi times x minus 0 squared dx. And I'm getting 67.021. 67.021. Now hold up a minute. What was our answer here? Bingo. Check this out. This is what's so awesome about this lesson. I get excited about this lesson. Up here we found volume of a cone by geometry. Down here we found volume of a cone completely differently by finding a cross-section of the 3D figure, making an infinite number of such cross-sections called disks, adding all the volumes of said disks together to get total volume. Totally different method than geometry. This is what separates calculus from the rest of mathematical studies. Calculus is going to enable us to find volume of figures, three-dimensional figures that geometry could not. Okay, let's look at example 3. Example 3 says, find the volume of a cone with a radius of 2 and a height of 4 using geometry. Again, there's the equation. So I'm going to plug in my stuff. Volume is 1/3 pi, radius 2, height 4. Height 4. So let's see what that is by geometry. So I've got 1/3 pi times 2 squared times 4. Okay, I'm getting 16.755. Okay. Now, oh, by the way, guys, I forgot to mention up here, if you were confused as to why those came out the same, I'm sorry, I forgot to mention, if you look at this cone, do you see the criteria here? This guy had a radius of 4 and a height of 4. Well, what does this guy have? He's got a height of 4 and a radius of 4. So height 4, radius 4. So it's the same dimensions on that cone. Should have mentioned that. So I'm guessing that example 4 is going to have a radius of 2 and a height of 4, and we're going to end up getting the same answer. Let's see if we do. So example 4 says, find the volume of the solid generated when the region bounded by y equals 2x and the y-axis from y equals 0 to y equals 4 is revolved about the y-axis. So this time, I already drew it. I've got my y equals 2x here, my y-axis, and then from y equals 0 to y equals 4, I've got that all shaded in. I'm going to rotate around the y-axis, and then I'm going to mirror this or reflect it across the y-axis. So it's going to look like this. And hopefully you can tell that this is going to create in 3D, if I spin this section around and around and around and around, it's going to create yet another cone. This time the cone has a radius of 2, bingo, and a height of 4, bingo. So I'm going to try to get the same answer, 16.755, using calculus. So I've got to think of my cross sections. Well, you always want to take your, I say knife or whatever, and cut perpendicular to the axis you're spinning around. So if I'm spinning around the y, my cut goes like this. So imagine cutting and looking inside, you would see a disc. A circle with a little bit of thickness here. Let me draw that thickness in there. There's your thickness. Now the thickness, interestingly this time, follows and is parallel to the y-axis, so this is going to be a thickness of dy. So the volume then of my entire cone can be found by adding up, summing up, that's sigma, from 0 to 4. Now, these are y values now. From 0 to 4, the volume of a disk. And we know the volume of a disk is the area of the base, pi r squared, times the height. Or, in our case, since we know our height right here is just this little change in y, we'll say dy. Now, the only thing you got to keep in mind with y-axis revolution is that everything that you put into this formula must be in terms of y. So the 0 and the 4, those are y values. The height, dy. So this radius right here of any disk, we have to get it in terms of r, or in terms of y. I'm sorry, it already is in terms of r. We need to get it in terms of y. So let's take a look at the radius. Just look at this cross section. Do you see how the radius is measured from the y-axis, which is the center, over to the right? And that distance is determined by this line, y equals 2x. Well, here's the interesting thing. The radius right here, that's not a y value. This is horizontal. This radius is an x value. So like if I pull this cross section out here like this, right? You're going this way, that's an x. So we need to basically take the equation y equals 2x and just solve it for x equals. So if I just divide by 2, then x is equal to y over 2. So every radius, whether little or big, every cross-section radius is determined by x equals y over 2. And it will increase in value as you go up the cone because it's following the contour of this line. So that's what I have to put in for r. So to finish this problem, v will equal the definite integral from 0 to 4 of pi times y over 2. Oh, messed up already. Scratch it, scratch it. Because I forgot that thing up here about the minus 0. See, even I tend to forget it. Make sure for future reference, it's the right minus the left. But since the left here is x equals 0, here's how we'll write it. You ready? V equals definite integral from 0 to 4 of pi times the right, which is y over 2, minus 0 squared dy. Okay, now when we put it into the calculator, you can use y. I mean, you can certainly do alpha. Where's the y? Where's the y? There it is. You can use alpha y. Bring that down. But I don't bother. As long as this is set up correctly on my paper, the calculator doesn't care if you put y or x in. So I'm just going to put an x in. So math 9, let's bring this over. Math 9, definite integral 0 to 4 of pi times alpha y equals x over 2 minus 0 squared, and then dx. And look what I get. 16.755, the exact same answer that I got up here. They match. Awesome. All right, I'm going to stop this video here because this first video took a little bit longer because I had to talk all about cross sections and sigma. So what I'm going to do is pause this video. There is a backside, but the next video, we'll call it part 2, is going to take care of the backside. Okay, so thanks for watching.